Hi, I'm Manesh, and today I'm going to talk about our work, Bit Exact ECC Recovery, BEER, determining DRAM OnDie ECC functions by exploiting DRAM data retention characteristics. This work was done by researchers in the Safari group at ETH Zurich and is presented in the memory session at Micro 2020. First, I'm going to start out with a high-level summary of this talk. The problem that we tackle in this work is that DRAM OnDie ECC complicates third-party reliability studies. This is because its proprietary design obfuscates raw bit errors in an unpredictable way, and this interferes with design, test and validation, and characterization studies. To overcome this problem, our goal in this work is to understand exactly how OnDie ECC obfuscates errors. And to achieve this goal, we make two contributions in this work. First, we introduce BEER, a new testing methodology that determines a DRAM chip's unique OnDie ECC function. In other words, its parity check matrix. BEER exploits ECC function-specific uncorrectable error patterns and requires no hardware support, inside knowledge, or metadata access. Our second contribution is BEEP, which is a new error profiling methodology that infers the raw bit error locations of error-prone cells from only the observable uncorrectable errors. We evaluate BEER by experimentally applying it to 80 real LPDDR4 DRAM chips from 3 major DRAM manufacturers, and we show BEER's correctness in simulation for over 100,000 representative OnDie ECC codes. And finally, we hope that both BEER and BEEP enable many valuable studies going forward. So here's a high-level outline of my talk. First, I'm going to start out by talking about the challenges caused by unknown OnDie ECCs. Here is a typical OnDie ECC code used in modern DRAM chips, and this is typically a 128-bit single error correcting Hamming code. Here's an illustration of what this code looks like within a real DRAM chip. And we see that the encoder and decoder, which together form the ECC logic, are fully contained within the DRAM chip. And this means that they are completely invisible outside the DRAM chip. Now, there are many ways to implement this 128-bit Hamming code, and these correspond to using different ECC functions, which are known as parity check matrices, or H matrices. Now, all of these ECC functions correct one error, but they act differently on 2 or more errors. Manufacturers are free to choose any design they wish for this ECC function, and they may choose to do so based on circuit optimization goals, for example, layout area or power consumption, and the details of a particular implementation are considered highly proprietary, even under non-disclosure agreements. Now let's take a look at the effect of using different OnDie ECC designs. In this experiment, we simulate uniform random errors within a single 32-bit ECC word. In this figure, the x-axis shows the bit index in the 32-bit ECC word, and the y-axis shows a relative probability of observing an error in each of the different bit positions. Now, because we simulate uniform random errors, the per-bit error probabilities are roughly equal to each other for each bit position. However, the post-correction errors look quite different. Here we show 3 different 32-bit Hamming codes, each of which uses a different parity check matrix. And we see that the post-correction errors are highly non-uniform and depend on the particular ECC function used for that curve. Our takeaway from this analysis is that the same error characteristics can appear very different with different ECC functions. So this causes significant challenges for third parties who need to understand DRAM reliability characteristics in order to do their work. For example, system architects typically design error mitigation mechanisms at the system level to meet overall reliability targets. However, with OnDie ECC forces them to support unpredictable chip-dependent memory reliability characteristics. Test and validation engineers often perform extensive post-manufacturing testing. Unfortunately, OnDie ECC hides the root causes of uncorrectable errors and defeats test patterns that are designed to target physical cells. And finally, research scientists typically perform error characterization studies to understand how DRAM chips work. Unfortunately, OnDie ECC conflates raw bit errors with ECC artifacts, effectively obfuscating the true physical cell characteristics. Now, these challenges all arise from the inability to predict how ECC transforms error patterns. And to overcome these challenges, our goal in this work is to determine the OnDie ECC function without hardware support or tools, prior knowledge about OnDie ECC, or access to ECC metadata, for example, error syndromes. And what this means in the context of a real DRAM chip is that we want to know exactly what happens within the ECC encoder and decoder, because this would reveal exactly how OnDie ECC scrambles errors and would allow us to infer raw bit error locations just by looking at the post-correction errors. And we'll talk about both of these aspects later in this talk. Now this leads us into our primary contribution, called BEER. BEER determines the ECC function using the key idea that we can identify the ECC function based on how it responds to uncorrectable data retention errors. Now, Data retention errors are relatively easy to induce. Using a CPU or FPGA, we can simply pause DRAM refresh. And the figure on the right shows exactly how this affects a single DRAM cell. So the x-axis here shows time, and the y-axis shows the cell voltage. And we see that a single cell that starts out in the charge state loses charge over time naturally. Although periodic refresh operations maintain this charge value, once we pause DRAM refresh, the cell voltage drops below the safe voltage value, beyond which we can no longer identify the initial value that was stored in the cell. And this results in a data retention error. In contrast, a cell that starts out in the discharge state remains in the discharge state for all time. And this difference between the charged and discharged cells allows us to restrict errors to specific bit positions. For example, let's consider a test pattern with only one cell charged. After ECC encoding, we have only one charged cell within the data portion and 3 unknown parity check bits. Note that we assume here that the data is stored unmodified, and this corresponds to a systematic encoding, which is typical of real memory devices. Now, in this encoded data, we have effectively restricted possible data retention errors to specific bits. In this case, the charged bit and any possible charged bits within the parity check bits themselves. So let's take a look at what happens when we induce data retention errors. Let's suppose that we start with the same test pattern as in the previous slide, but we now know that the ECC function sets precisely one parity check bit to the charged state. When we go ahead and induce data retention errors, there are several different pre-correction error patterns that might occur. For example, we might have the case of no error. We might have the case of a correctable error where a single charged bit flips to the discharge state. And finally, we can have an uncorrectable error pattern where both charged bits flip to the discharge state. In this case, depending on the particular ECC function that OnDie ECC uses, the ECC decoder might result in any of 4 possible different data patterns. And this means that different H matrices cause different uncorrectable error patterns. And we can differentiate different ECC functions based on their uncorrectable error patterns. Now we simply need to choose a set of test patterns to use for our analysis. And in our work, we consider the n charged test patterns, each of which sets n bits to the charge state. Now our paper explains that the combined 1 and 2 charge test patterns suffice to identify the ECC function. And in order to test each of the patterns that we use, we find all possible uncorrectable errors that can occur with that test pattern. This is easily done by exploiting the uniform randomness of data retention errors. For example, even one DRAM chip provides millions of samples to test from, and by looking at all of the different ECC words within a DRAM chip, we can get a sample of all of the different possible uncorrectable errors that might occur. Now we put this together into a 3-step testing methodology that we call BEER. The first step is to experimentally induce data retention errors using the combined 1 and 2 charge test patterns. The second step is that for each test pattern, we identify all possible uncorrectable errors that might occur. And finally, we solve for the ECC function responsible for the observed errors by using a SAT solver. Now I'll cover our evaluations of BEER in both experiment and in simulation. So first I'll cover our experimental methodology. We test 80 real LPDDR4 DRAM chips from 3 major DRAM manufacturers whom we anonymize as A, B, and C for confidentiality reasons. We conduct all of our testing in a temperature-controlled testing infrastructure that provides fine granularity control over DRAM timings, including those of DRAM refresh. We test refresh windows between 1 and 30 minutes at temperatures of between 30 and 80 degrees centigrade, and this leads to relatively high bit error rates between 10 to the minus 7 and 10 to the minus 3. And these bit error rates are high enough to subsume any errors we might get from background noise and other error mechanisms that might interfere with our tests, for example, spurious soft errors. Now let's take a look at what happens when we apply BEER to real DRAM chips. In this experiment, we study the uncorrectable errors in the 1 charge test patterns only. Now in these figures, we show the uncorrectable errors for a representative chip from each of the 3 different manufacturers labeled as A, B, and C. The x-axis for each figure shows the bit index within a 128-bit ECC data word, and the y-axis shows each of the 128 1-charge test patterns, as indexed by the position of the charged bit in that test pattern. Now the first thing we notice are the data retention errors along the y equals x line, and these correspond to normal data retention errors from bits in the charge state flipping to the discharge state. Any errors off the y equals x line are miscorrections that are purely an artifact of ECC correction, since they correspond to discharge data bit positions. Now by comparing each of these 3 plots, we see that there's a high variation between each of the 3 error profiles from the different manufacturers, and this indicates that they likely use different ECC functions. And finally, we notice repeating patterns within the miscorrections of manufacturers B and C, which indicates underlying structure in their H matrices, which appears to be absent in the profile of manufacturer A. Now we have two key takeaways from this analysis. First, we note that different manufacturers appear to use different OnDie ECC functions. Second, although not shown in this data, we show in our paper that chips of the same model number appear to use identical ECC functions. So the next step is to identify the specific H matrix that each chip uses, and we do so using the Z3 SAT solver. Although in our work we demonstrate and evaluate Beer for single error correcting Hamming codes, Beer readily applies to all linear block codes, including, for example, BCH codes and Reed-Solomon codes. We open source our Beer implementation for any end user to make use of on GitHub at this link. Unfortunately, we face two limitations in our experimental studies to further validation. The first is that we have no way to check the final results of our analysis, since we cannot see into the OnDie ECC implementation and look at the final H matrix that actually exists within the chip. And the second limitation is that we cannot share our final matrices due to confidentiality reasons with the manufacturers. Therefore, to overcome these limitations, we validate Beer in simulation, which allows us to evaluate Beer's correctness, to overcome confidentiality issues we face in our experiments, and to test a much larger set of ECC codes. So now we'll talk about our simulation methodology. We use the EinSim DRAM error correction simulator to simulate injecting data retention errors. And we simulate over 100,000 different single error correcting Hamming codes that are representative of OnDie ECC, with ECC data word lengths ranging from 4 to 247 bits. We use the 1, 2, 3, and combined 1 and 2 charge test patterns in our analyses. For each test pattern that we simulate 10 to the 9 ECC words and data retention error rates with bit error rates between 10 to the minus 5 and 10 to the minus 2, which approximate those of our real experiments with actual DRAM chips. Now let's take a look at our correctness evaluation for Beer. In this experiment, we evaluate the number of unique SAT solutions that Beer finds, and this shows whether the unique ground truth solution is identified. In this figure, the x-axis shows the ECC code data word length, and the y-axis shows the number of unique ECC functions identified for all of the different ECC codes that we simulate. Each data point shows the minimum, median, and maximum values observed across all of our simulated ECC codes. The first thing we notice is that the 1 and 2 charge test patterns that here are pictured in red, combined, they always find a single unique solution for all test cases. We also see that the 1, 2, and 3 charge test patterns individually sometimes find more than one ECC function that can explain the observed uncorrectable errors. Now our takeaway from this analysis is that Beer successfully identifies the ECC function using the combined 1 and 2 charge test patterns for all test cases. Finally, I'd like to talk about beep and other practical use cases for Beer. In our paper, we provide 5 use cases to show how knowing the ECC function is useful in practice. The first use case deals with error profiling, and we introduce beep, which shows how knowing the ECC function enables us to identify raw bit error locations that correspond to observed post-correction errors. Our second use case deals with system design, where knowing the ECC function enables the system architect to design DRAM controller error mitigations that are better informed about OnDie ECC and a DRAM chip's reliability characteristics. Our third and fourth use cases deal with testing, where knowing the ECC function enables crafting worst-case test patterns to enable efficient testing and validation, and better perform root cause analyses for uncorrectable errors. And our final use case deals with error characterization, where knowing the ECC function enables better studying the statistical properties of raw bit errors, for example, their spatial distributions. Now, our paper contains a wealth of other information that I did not have time to delve into here today, and this includes formalism for Beer and the N-charge test patterns that we briefly talked about. We have more evaluations for Beer in both experiment and simulation, including sensitivity analyses to experimental noise, an analysis of experimental runtime, and an analysis of practicality of the SAT problem, including both runtime and memory usage. We evaluate beep in simulation, showing its accuracy at different error rates and its sensitivity to different ECC codes and word sizes. We provide a detailed discussion of use cases for Beer, and finally we provide a discussion on Beer's requirements and limitations in practice. Finally, I'd like to circle back with a summary of our work. So the problem that we tackle in this work is that DRAM OnDie ECC complicates third-party reliability studies, and to overcome this problem, our goal in this work is to understand exactly how OnDie ECC obfuscates errors. To achieve this goal, we make 2 main contributions. First, we introduce Beer, which is a new testing methodology that determines a DRAM chip's unique OnDie ECC function, in other words, its parity check matrix. And our second contribution is beep, which is a new error profiling methodology that infers the raw bit error locations of error-prone cells from only the observable uncorrectable errors. We evaluate Beer in both experiment and simulation to show its effectiveness and practicality, and we open source our implementation on GitHub at the link shown on the slide. Finally, we hope that both Beer and Beep enable many valuable studies going forward. Thank you, and if you enjoyed my talk, please take a look at our full paper.